Can you hear me now? Yes. Dear all, ladies and gentlemen, it's as usual a pleasure to welcome you to our webinar, and this time to our global symposium on recent advancement and the way forward in confined masonry construction practice. We have a packed agenda today and tomorrow, and we expect quite a sizable audience with whom we will exchange ideas through these 3 hours today and 3 hours tomorrow. We also have a packed line of speakers, 15 speakers from 15 different countries, and 5 reactors, which will be with us throughout the presentations, and they will help us in the general debate. We will present people from the speakers as we come in, but you can have an idea of who they are in these slides. And then I would just like to walk you through our program today. So I will give a very brief introduction to the symposium just to set the scene. And then we have here our guest speaker, Professor Svetlana Brest, a joint professor at Columbia University, British Columbia University in Vancouver. And she will speak about application of confined masonry technology, a global perspective, and the status of designs code. She has been the EARIDE confined masonry network chair for many years, and she has truly a global and overview of where we are with the in the introduction of confined masonry and to the dissemination of confined masonry. We will have a very brief question and answers, and then we will move to summary and advancement in research in the field of confined masonry. So we have 2 very interesting intervention here. One that looks more at the applications of codes for the design and analysis of confined masonry by Vaibhav Singhal, and then a more academic view on research, but still research that find direct applications in practice by Juan José Pérez Gavilán. Some more question and answers if there is any arising, and then we will have a coffee break. Virtual, unfortunately, we will not be able to offer you anything, but we hope that you are ready there with your coffee cups or whatever other drink you prefer. And then we will go on to our first debate and period on open, there will be an open discussion on the gaps in the design coded in the research, which will be moderated by Professor Svetlana Brest and Professor Sergio Alcocer. We will then move on to the second part of the afternoon, looking at confined masonry for school constructions. So here we will look at applications from and challenges from different parts of the world. As you can see, we have speakers from Indonesia, Kyrgyzstan, Peru, Mexico. And also we will present from our point of view the work that we have done again at a global level on the glossy taxonomy for confined masonry. We will introduce the speakers of this second part as we start the second portion. After that, there will be a panel discussions again on school applications, on application of confined masonry to school structures and to school buildings. So we are really here interested in hearing from all participants on their experience, if any, or their point of view in considering in considering the application of confined masonry to school structures. What are the problems? What are the issues? And this panel discussion will be moderated by Asana Paramalvattelli from UCL and Anna from Bill Change. For tomorrow, you will have an opportunity to see more of this. So we have an introduction to the second days that will be much shorter than this one. But tomorrow we will concentrate on retrofitting and adaptations. So cases from mainly from Mexico, Colombia, and Indonesia. And then we will look at the point of view of the durability and climate adaptation of confined masonry construction. Is confined masonry durable, but is it also a more sustainable way of building that indeed current reinforced concrete or unreinforced masonry or reinforced masonry. So we will look into that in quite a little bit of details with Sebastian Kaminski and Anna Pavan. After the coffee breaks, we will have reactions from our panel of reactor, and then we will have an open discussions that aims to summarize both the discussion that we have today and any other issue that will be raised tomorrow. Now that I have briefly given you an overview of the program, I hope that you will enjoy it. I just want to take a minute of reflection here because 2 days ago was the first anniversary of the Turkey-Syria earthquake, which occurred in 6 February 2023. Although we call it one earthquake, there were at least 2 very strong motions in the space of a few hours, and then a third strong motions a few days afterwards. And these maps just give you the idea of the extent of the geographic extent of the area that was badly hit. Indeed, 11 provinces were substantially affected. I don't want to go through the reason for the results of what we see in the image, but I just would like to point very shortly to the fact that in Turkey, about 20,000 educational buildings have been affected, are in the region that have been affected. Of these, about 1,842 were either destroyed or had severe or had a certain level of damage. But as you can see, it's less than 10% of the building, school building, were totally affected. That notwithstanding, it is assumed that the funding required to take these schools and institutions back to where they were would be more than $2 billion of US dollar. Schools performed in different way, as you can see here, but as we celebrate the first academic, the first let's say, anniversary of the earthquake, we are also reflecting on the fact that 30% of the children that have been, students that have been affected by the earthquake still have not access to full education. And for 20% of the Turkish citizens name a lack of funding in order that or financial constraints that prevent school. But in Turkey, as well as we will see later, one of the major things that happened after 1 month of closure of the school after the earthquake was to plan the, let's say, traveling of students and mobilization of students to safer school away from their region. And this phenomenon is increasing as an element of recovering of the education disruptions in various countries. Here, I just want to speak very briefly of the Morocco earthquake that hit the Amis regions on 8 September 2023, about 7 months later than the earthquake in Turkey. It was clearly a smaller earthquake, not just in magnitude, but also in death toll. About less than 3,000 people were killed and 5,000 injured. But the earthquake damaged many villages and cities in these areas. And these are two pictures from schools that were damaged. Here you can see that they are a mixture of concrete and masonry structures in each of them. In one case, rubble masonry, in the other one, more confined masonry. But of the 530 educational institutions that were affected and damaged to various levels, then many of them are still took several months to start again, to resume educations. And in many cases, again, students had to travel from their villages to farther afield in order to attend temporary schools in tent, as much as 15 kilometers daily, or indeed move to other villages without their relative or parent. And finally, just a very quick resume of the earthquake that occurred in Japan. We are now, again, about just 1 month from the event. And you have some statistics here where of the 270 schools and facilities were damaged, and in 20 cases also damage to important cultural assets. But moreover, 39 schools were also used for evacuation centers, such as, for instance, the school in Wayajima and the school in Kanazawa, where although they were not damaged directly, there were some very important soil failures that made the school inaccessible. And again, in this case as well, students have been mobilized from, for instance, Wajima, Suzu, and Noto to other locations where the schools had survived in better conditions. So as part of this type of event, we have been looking as part of the UNESCO chair at what does it mean to minimize the disruptions of education following an earthquake or another natural hazards. And we are focused on the school portfolio of the Dominican Republic in this Berlac project, which was managed by UNESCO. You can read more about what the type of analysis and the type of identification of actions that can reduce that interruption you can find at this particular website. So what is the way forward? Can indeed confined masonry be the answers to the problem of having relatively large school buildings, which are not too expensive to build in developing country, but that remain reliable and can be occupied immediately after an earthquake? One of the efforts that we did through the glossy projects, which Dr. Sana Paramal-Valteri will expose later today, was to try to identify some very simple constructional elements that would allow us to qualify the level of seismic design that is associated with them, and therefore be able to identify whether a school is indeed capable of withstand an earthquake of a given magnitude or not. So these and many other issues that will be raised during the next few presentations we can debate later on after the break. But now I would like to leave you with the future program of events that we will have in the future months, and at the same time we invite to the microphone Professor Svetlana Brev, again, adjunct professor at the University of British Columbia in Vancouver and chair of the Confined Masonry Network of ERI. Svetlana, please.
Thank you very much, Dina. It's a pleasure to be invited to participate in this event. I would like to thank I would like to use video if possible. It says I cannot use it. If I can, and I'll share screen. Okay, just a moment, please. Okay, so screen. Can you see the? Yes. Okay. Okay. So the only thing is video is not possible. It's I think okay. So I don't have a video, but I would like to welcome to thank you for participating in this event. My name is Svetlana Berzev, and I am I've been working in the field of confined masonry for many years. I hope maybe you can see me now or not. Maybe not. I would like to, today the topic of my presentation will be applications of confined masonry technology around the world, and also about the global perspective and status of design codes and guidelines. I would like to thank my collaborators who have been working with me on the code review issues, a joint group from the Masonry Society and ERI. We have been working together for the last few years. Matthew Reiter, Juan Jose Perez Galvilan, Daniel Quinn, Eric Espinoza, Sarah Ganserly, Tim Hart, and Mark Membreno. And because a part of today's presentation will be based on our work. So the topics that since my presentation is the first one today, I will first start why do we use confined masonry very briefly. I think that is clear. Then about what is unique about confined masonry, and then about international applications, design codes, and guidelines. So lots of topics in a little time. But I'll try to make it within the time frame. So why confined masonry? Even though this is not such a new situation, I mean it's been repeating after every earthquake. I like the comparison of the January 2010 Haiti earthquake, in which, I mean, it's not been determined, but more than 200,000 to 300,000 people died due to poorly constructed concrete construction. practice, and it was a tragic event, magnitude 7. Almost at the same time, or 2 months later, on February 27, the same year, 2010, a magnitude 8.8 earthquake struck Chile. In that earthquake, which was extremely powerful, there were 521 deaths, out of them 100 due to tsunami. In that earthquake, many confined masonry buildings have been exposed because it is a prevalent construction practice in Chile for residential, low to medium rise residential buildings. So, and there are other earthquakes, just to mention a few. For example, in Peru, there was magnitude 8 earthquake in 2007 in Pisco, where confined masonry performed well. It's been practiced in that country, and there is a code. And similarly in El Salvador, again, those are photographs of standing buildings, which are obviously confined masonry, where the surrounding buildings are vulnerable types, such as, sorry, adobe or other forms of unreinforced masonry. So the key features of confined masonry are the masonry walls, because it's load-bearing masonry construction. It's always important to emphasize that and not to forget. But it is reinforced by horizontal and vertical reinforced concrete elements, which are called confining elements, or vertical elements are called tie columns, and horizontal tie beams, to have a link verbally with columns and the beams in reinforced concrete construction, but they are really different. They have different roles, so to speak. In this case, confining elements their role is to resist axial loads, tension, compression, and these confining elements, for that reason, are smaller than columns and beams in reinforced concrete frame construction. Here is an example of a reinforced concrete building in Petrinja, Croatia, which withstood the December 29, 2020 earthquake, magnitude 6.4, without any damage. It is constructed according to European, I would say, principles of practice, Euro codes, which have provisions for confined masonry for many years, and also previous codes in Croatia had that. So components are masonry walls, which is marked red. Blue are vertical confining elements, tie columns, which are shown at framing this big opening, door opening at the ground floor, and also at the wall intersection, and horizontal confining elements, so-called tie beams, usually at the floor levels. So the question is, what are these distinctive features of confined masonry? You could see it now, and just for those of you who are not familiar, first is that it is load-bearing construction. The second is construction sequence, the way confined masonry is being built. Third is layout of these vertical confining elements, particularly tie columns. And the fourth one is interface between masonry and concrete in this system. So I'm using here some graphics from my good colleague and architect, who has really nice way of showing maybe complicated things in a nice graphical way. One is the first. This is a comparison or the illustration that confined masonry is a load-bearing structure, and if lateral forces are applied to a confined masonry wall, shear is mostly resisted by masonry wall, with some contribution from these vertical elements, whereas bending, the resulting bending effects are resisted by tie columns, plus, of course, partially by masonry acting in compression. Whereas if you have reinforced concrete frame, here it is shown without any infills, which is actually the system that is being used in many countries and has not performed well. In that system, we don't need a wall, because this frame should stand on its own. It should be able to resist the effects of axial loads, shear, and bending on its own. So that is a big difference between those two systems. Sequence of construction in confined masonry: walls are constructed first, and then these vertically reinforced tie columns are being concrete in those elements has been placed gradually, floor by floor, or even less. And on the left-hand side and on the right-hand side, we have a concrete frame reinforced concrete frame in which we first construct a frame and then masonry infills or masonry partition walls, exterior walls are constructed later. So this is essential difference, and it has implications on behavior of these two systems. In confined masonry, the layout of this vertical element is recognizable. Oftentimes, colleagues ask, how do we recognize that this is confined masonry and not reinforced, not frame building? One, if confined masonry is properly planned, building is properly planned, we will see that we have some intermediate tie columns in between the walls, like marked 6 or number 6 here. Then we would have some tie columns at the ends of the walls, which cannot marked 4 on this drawing, which don't align with this intermediate or number 6. So you can see they're really all in a sense random, but they have a meaning. So the main purpose of these elements, vertical elements, and the way the philosophy behind placing them is that they have to confine, they have to be placed on both sides of a masonry wall, and that is their role. So anyways, that is unique. And the fourth characteristic, which I believe is often debated among experts in confined masonry, is it needed or not? And that is the type of interface between masonry and concrete, and that is so-called toothing. So on the left-hand side, you can see a toothed connection where you have like this exposed bricks, and then when concrete is poured, like on this drawing shown grade on the drawings, you can see that there is some form of shear key that is being formed between concrete and masonry, and that helps improve the bond between, of course, masonry and concrete. Alternatively, in the modern construction practice, more and more bricks are being phased out, but instead of them, we use modular blocks. And in this system, we have we cannot place easily those tooths or toothing. So we have this reinforcement, horizontal reinforcement, which is being placed in between running through these tie columns, but it has to be anchored to the left and right on both sides in order to achieve, again, equivalent bond, so to speak. Many codes, for example, Euro code, contain provisions that enable, and other codes that offer this alternative, so to speak. Confined masonry applications around the world. International practice is such that confined masonry has been used for more than 100 years. First application, reported application, so to speak, was after the 1908 Messina earthquake in Sicily, where it has performed well, and that's how, was, without engineering input, it was shown as a good example of practice to be followed. And somehow, even though transportation means were very different than today, it somehow was moved to Latin America in 1930s already, and where the first confined masonry buildings were exposed to some of the powerful earthquakes in countries like Chile and later on Mexico. And it has been used ever since. And I would say encouraged, its application was encouraged those countries. What is characteristic for confined masonry, that it has been practiced, which is positive in seismically active and hurricane-prone regions. And there are also both engineered and non-engineered applications of this technology. Many houses are single-family houses and non-engineered applications, but there are apartment buildings in countries like Peru, Chile, and other Mexico, which are, of course, engineered, designed by engineers. Mostly confined masonry buildings are residential applications, but as we will hear at this symposium, and as we know, they're also used for constructions of schools. On this map on the right-hand side is an effort to show where confined masonry has been used, shaded in brown. It was developed by my colleague Kea Mitra and I, published in our publication, but maybe there are more the countries that we have missed. We are focused on just showcase a few countries. On the following slides, I'm sorry, it's no time to talk about all. So left-hand side is Mexico, and very nice advanced application of actually metal formwork in constructing a confined masonry building. We can see with the concrete block construction as masonry elements. It's important to know that besides clay elements, we can use concrete as well, as long as it is a good quality. Middle photograph is Chile, typical apartment building in Chile. It's actually social housing that the government has constructed for people, and many people live, they're occupied, a large percent of population in Chile lives in these buildings. And on the right-hand side is an example from Colombia, low-rise building. Again, Colombia is one of the countries, and I'm sorry, I haven't missed others. So I would say highlight of this is significant applications of confined masonry technology and well-established design codes with long history in Latin American countries. Then we have countries like, for example, Indonesia, which is shown on the left, those two photographs, which has more than 40 years of history of confined masonry practice, but there is, according to my knowledge, there is not yet a design code in place for confined masonry. On the right-hand side, we have Iran, just one photograph from Iran, again, a country that has been using confined masonry and is addressed in the code in some way. Now we are coming to Europe. I am originally from, as many of you know, I'm from Serbia, territory former Yugoslavia. And in our country and in the region, confined masonry has been used since the first seismic code of the country in 1964. And this on the left-hand side, we can see some photographs from Slovenia. And you can see again use of clay, hollow clay blocks, modular blocks. And on the right-hand side is photograph from Croatia. This is actually not a good example. I showed another good example at the beginning, a very good example with excellent performance. This is, I want to use, even though the short time, to show what happens if you don't follow practice. So it's not like flowery picture of all excellent performance. It depends on the practice. This is an example of buildings in Croatia that did not implement confined masonry to the ground floor, but they extended the building vertically, and then they introduced confined masonry. Of course, that building did not perform well, but normally it is not a desirable practice, and it is one example of poor performance in the 2020 earthquake, which hit Petrinja in Croatia. Now I'm coming to India, a country which I like very much and have spent a substantial amount of time working and teaching, actually, in confined masonry at IIT Gandhinagar and other universities. And it is a country in which confined masonry is, we can say, recently introduced. Recently, we can say in the last 10, 15 years. But positive is that in 2022, there was the code, the first Indian code was issued related to confined masonry. And previously, there is a history of informal confined masonry applications. These two photographs are showing a first formal application of engineered application of confined masonry in India on the campus of IIT Gandhinagar. What is characteristic for India, and I would like to say this is a uniqueness of Indian practice, is that in confined masonry buildings, there are always bands, or at least that is the code requires, bands on the lintel level, for example, and possibly in some other levels, in addition to horizontal tie beam, which is at the floor level. So international design codes, a brief just overview. We'll have more opportunity to hear about design from the subsequent speakers. I would like to say this group that I mentioned at the beginning, and I have been working on a code review for the last few years. And we're looking at what are the key parameters that we would compare that would identify are important for confined masonry. And we wanted to see how codes address them. So they are listed here. One is wall slenderness. The other is in-plane resistance, let's say, to shear and flexure, design for shear and flexure. With flexure, we always have also axial load, of course. Then out-of-plane resistance of these walls, design of walls with openings, then wall density, amount of walls in a specific direction, like percentage, design and detailing of these concrete confining elements, spacing of the confining elements, and material properties given that it is load-bearing construction. So looking at the building, this is the building from Peru. We always are looking for actions, seismic actions in plane, out of plane, and how to design a wall. Do we have a tool? Do we have approach? Or it is just prescriptive based on some rules? So this is a comparison of the codes. It is been published. In fact, I will include the full name of the title and maybe possibly the whole paper that was published at the conference a few years ago. But you can see here, in fact, difficult now to digest in the short time, but just to say that we consider codes from Argentina, Chile, China, Colombia, Eurocode, and Mexico, Peru, and Peru and Kyrgyzstan as an example of the former Soviet Union or CIS countries. Then we rank them by number 1, 2, 3, where 1 means a very low level of coverage for that particular provision, and 3 means maximum. And then letters A and P, where A means analytical approach to specific provision, and P means prescriptive. So on the next slide, I will show what, in our opinion, was the coverage. What is green is good, like this is well covered, I mean, defined and reasonable. And you can see wall slenderness, in plane resistance, and so on is good. Design detailing of confining elements, but what is missing from the codes, most codes, out of plane approach for addressing out of plane resistance of confined masonry, and also design of confined masonry walls with openings. And wall density or wall index is covered in some codes. In others, it's simply they don't want approximate methods such as that one, and that may be the reason it is not covered. So red ones are the ones that are missing and are important aspects. Finally, the last topic is international CM guidelines. Most of the guidelines are focused on on construction, actually. So one of the first guidelines, and my favorite at that time, was led by my colleague and friend Marcial Blondet in Peru back in 2005, and it was wonderful graphical guideline, still published, available. Then there were some Colombian guidelines, and also excellent cartoon done in Mexico. Then we have other guidelines done in other countries. I cannot mention all, but for example, Pakistan, done after the 2005 Kashmir earthquake. Then in Pakistan, in India, Tom Shaker, like Swiss group, Swiss colleagues, led by Tom Shaker, architect Tom Shaker, published again guidelines for construction of low-rise confined masonry buildings, and the same guideline was published in India. And I have done the first monograph in India, which was currently available through NICE, but the old version was 2007, the new version in 2018 with Professor K.M. Mitra. So if you're interested, you can access it free of charge. And I would like to mention that other guidelines, they were definitely worth mentioning, but no time to discuss, were developed by Build Change, CBRI in India, Research Institute, and some practicing engineers like late Teddy Bowen in Indonesia. Confined Masonry Network organization that I belong to, or a group of professionals, was started by ERI in 2008. And our role has been to develop different guidelines. And the first one was design guideline on the left, published in 2011 for low-rise buildings. Then the second is guidebook, again, in collaboration with Swiss colleagues for builders. And the third is guideline, very detailed guideline for construction, again, by Tom Shaker and Tim Hart. So, so these guidelines are available free of charge on the Confined Masonry Network's website, so you can access them if you're interested, and there is other resources and good information. In conclusion, I would say it's obvious confined masonry construction has been practiced in many countries across several continents. It's well-developed technology and well-established in many places. If properly designed and constructed, these buildings can perform well and have performed well in past earthquakes, and good examples should be followed. There are variations in construction practice, but they're not too significant between countries. Most countries in which confined masonry construction has been practiced have well-established design codes, but the level of code provision definitely varies between the countries. And there are also several guidelines which are very useful for design and particularly construction of low-rise confined masonry buildings. Usually they're prescriptive, obviously, and are in place and are useful for builders of low-rise buildings and architects, other technicians. So that is all I wanted to share, and I hope I've not gone too much over time. Thank you very much. I'm standing here in Nepal in 2015, standing in 2015 earthquake where many reinforced concrete buildings, significant number collapsed. And the reason I'm showing this photograph, we want to avoid to see this in future. And we would like to promote confined masonry for low to mid-rise buildings where this application is feasible. Thank you very much. So right now, I think we'll introduce immediately the next speakers, or we have time for a few questions. We have the panel.
I think we can have any burning questions, one or two.
Okay, do we have any questions right now? We'll have a panel discussion after then. So if you don't have question right now, you can ask later. But if you have, I'm not sure if there is anybody on chat who would like to ask.
At the moment, no.
No. Okay.
There was a question about flexible concrete.
Oh, okay. So maybe then please think about questions and think of questions, and we'll have opportunity after the next two talks. Yeah. So I would like then with this to introduce the next speaker, my dear colleague, Professor Vaibhav Singhal from Indian Institute of Technology, Patna in India. Professor Singhal is a graduate of Indian Institute of Technology, Kanpur, and he has since he's and he is one of the first graduates in India who has done PhD on confined masonry. Actually, I'll stop sharing. Sorry, just to stop sharing. Okay. Sorry. Please share the screen, Vaibhav, and I'll just I would just like to say just a couple of words. He's a very active researcher in confined masonry, has published over 75 peer-reviewed papers in journals, and is a recipient of prestigious Serb International Research Experience Fellowship from Government of India. He is also one of the co-authors of the first Indian Code on Confined Masonry, and he's been actively involved in training courses and in promotion of confined masonry in India. So Vaibhav, please proceed. Thank you very much.
Yeah. So thank you, Professor Shatlana. So it is good to have an introduction from you. Really, it is kind of a touching because you are the main driving force introducing the confined masonry, and that small monograph was the first book which I read on confined masonry, and which drive me to do a research on confined masonry, to promote confined masonry in India. I hope I am audible and my screen is visible.
Yes.
Okay. Thank you. So today I will be talking about analysis and design of confined masonry. Primarily, I will be focusing mostly on the analysis part, and this is the work which I have done in collaboration with the IIT Guwahati, Professor Hemant Kaushik and his student. So I think Professor Brizeb has already introduced about the confined masonry. We have seen that confined masonry is now gaining popularity because of its some good advantages. It has better in-plane performance and better out-of-plane performance compared to the non-engineered reinforced concrete building and also the unreinforced masonry buildings. So when I started the work, so the question arises that how we can model them, how we can analyze and design the confined masonry buildings. Of course, some design guidelines are available. I will give some basic introduction also. Now, to make this confined masonry more popular, so we need to have appropriate numerical analysis tools also, so that the design engineers can use them and design the confined masonry for various level of forces. So a lot of work we have done, a massive experimental program. We have done numerical studies and also the analytical studies in collaboration with various institutes. So I will first discuss about the analysis approach. So to model or to analyze any confined masonry, the major task or major challenge is that how we can simulate or how we can create a model which can simulate both the gravity loads and the lateral loads. So one of the common technique or one of the, I can say, the easiest option which appears is detailed modeling using the finite element analysis. So the finite element analysis based on the availability of resources, one can go from a very detailed micro modeling to the simplified model, and then one can also go with a simple continuum or a micro model. And even the details such as like the reinforcement in tie elements, reinforcement in tie beams, and the interaction between the various surfaces can be simulated by using this finite element modeling. Now, there are some popular simplified models also, the second category, which is the simplified analysis techniques. So first one is the white column model. So white column model in which the confined masonry wall is simplified with a simple two-noded beam element joining the bottom and the top part, and other members can be also modeled accordingly. And then another method is the strut and tie method, strut and tie model, which is quite popularly used for the reinforced concrete members, which can also be implemented to confined masonry. I will discuss these techniques also in slide details in next slides. And then there are techniques like equivalent strut model or the equivalent shell model, which can also be used for the analysis and design of confined masonry buildings. Now, where the strut can be of a single strut, one can have multiple struts based on the level of accuracy and the level of forces which one has to simulate for the analysis of confined masonry walls. And at the last, of course, there are empirical methods. So empirical equations, analytical equations are also available for analyzing and for designing the various components of confined masonry. Now, coming to the limitations of various methods, the finite element method, especially, it requires large number of input parameters. One has to know about the constitutive models, the interaction between the various elements, interaction of reinforcement within concrete, interaction between the concrete and the masonry. And the simplified models also have limitations, especially in simulating both gravity and lateral forces, simulating the various failure modes, and also their applicability or expandability to the large scale buildings or to the real buildings. Now, just briefly discussing about the various methods so that various practicing engineers, I can see there are a lot of practicing engineers, they can know and they can use these various methods depending upon the convenience and the comfort level. The first method is the white column model, which is developed based on the concept of an equivalent frame model, which is commonly used for the unreinforced masonry walls, where the masonry wall is modeled as a one-dimensional two-noded centerline beam element, which is called as a white column. And then using the other properties, the transform section properties, the other elements can also be can be simulated in this assigned to the white column properties. The first application of this white column method was given in 2009, where this white column model was also used for simulating the complete load deformation curve, or one can say the pushover curve for the confined masonry walls. So where the input parameter, the hinges are defined at the critical location, and the input parameter is the load deformation curves for a various material using the various material properties. And this can be used to analyze and design the confined masonry walls. The strut and tie model, which is commonly used for the reinforced concrete shear walls or also for the shear critical structures of reinforced concrete. Now, the beauty of the strut and tie is that it can convert the complex structural member to the simplified truss model. So the concept was first introduced by Professor Brazil and Professor Gavilan, that how the strut and tie can be implemented for the analysis of confined masonry. Especially initially, it was introduced for the linear analysis for estimating the forces, and later a lot of work has been done. We have also worked on implementing this strut and tie model for analysis of confined masonry wall to find out their the limiting capacities, ultimate load carrying capacities. The major challenge is to define the limiting capacities of strut and ties for confined masonry. So the limiting capacity of a tie can be simply defined by using the yield strength of the reinforcement or the properties of the reinforcement, whereas the limiting strength of the strut is a major challenge, where because the confined masonry, depending upon the aspect ratio, depending upon the various properties, material properties, it can go into different failure modes. So one has to find out a way that how the limiting capacity of a strut can be simulated or can be found out. So based on the large number of parametric analysis, we suggested simplified equations, which can be used to find out the limiting capacity of a strut. And we have implemented these equations, and then we have found out that the strut method can be used to closely predict the experimental capacities also. And will be further extended to walls with openings. However, for walls with openings, one has to know the formation of a strut or the flow of stresses. Based on this basic knowledge, one can develop the student type for confined masonry wall with openings, and the predictions can be obtained very close to the experimental one. So this is also a good option which can be used for the analysis of confined masonry walls. Now, another interesting application of truss model, equivalent truss model, had been suggested recently by a research group from IIT Gandhinagar, where they have used uh, the properties, the force versus strain graphs to define to the truss elements, and which can be used also to find out the complete load deformation or the load drift response of a confined masonry building. So they have shown the application of this method. So the equivalent truss model, which is popularly used for the reinforced concrete masonry infill walls, can also be used for the confined masonry wall by using this level of simplifications. Uh, the equivalent shell model has not been very popularly used for confined masonry. It is primarily used for the linear analysis, where one can use the shell between the shell element defined between the reinforced concrete element, beam elements, for simulating the confined masonry buildings. There are different variations of also the equivalent strut, different level of depending on different level of accuracy. Researchers have suggested multiple struts for simulating the lateral response of or for simulating the horizontal response of confined masonry walls. Uh, we have also suggested another simplified model, which we call as the vertical and the diagonal strut model. So where we suggested that it is necessary to have two strut, the vertical strut for the gravity load, and also the diagonal strut to simulate the lateral load for the confined masonry walls, and some modifications on the beam element on the top horizontal beam, and based on the lot of linear analysis and comparison with the experiment, we initially suggested what could be the modifications required to these simplified elements so that simulate the initial stiffness and simulate the initial responses of confined masonry using this simplified vertical and diagonal strut model. Now, to implement this vertical, this VD strut model to simulate the nonlinear response, it is important to define the plastic hinges, like in the equivalent truss model or in the white column model. These hinges has been defined. So now the major challenge, as I said, especially it occurs to define the failure modes of the masonry, because the masonry can go into different failure modes depending upon the aspect ratio, depending upon the properties of various materials. So again, we go back to our finite element analysis. We did a lot of finite element analysis by calibrating the finite element model with the experimental results and changing with various parameters. We suggested a new term for simulating uh, the response of the masonry strut by using the term of effective shear strength, and suggested the set of equations depending upon the aspect ratio, which can be used to find out the nonlinear hinge properties for simulating the nonlinear response of the masonry. And using this VD strut model, using this new model, we have shown that the experimental response can be predicted very well. Here, one can see that the solid line shows the experimental curve, and the dotted line shows the pushover curve, which is obtained using this VD strut model. And we have also tested them on the multiple panels. And based on the 40 experimental studies, we have found that errors are nearly within 5% and also have a less standard deviation. So this can be a good option which can be used by the design engineers and which can be applied to the complete masonry buildings also. Now, one can also use these backbone curves for the analysis and design of confined masonry walls. So these backbone curves, generally they are developed based on the available experimental results, and some of these backbone curves, the limits of these backbone curves can be obtained, can be find out by using these equations which are available in literature. Now, in summary to this analysis method, so recently, like we have done the comparison of various analysis techniques to see the limitations and to see the level of the accuracy and the level of simplification of various analysis techniques. So we try to implement this various analysis techniques on a confined masonry building. So this is a model which is developed in SAP 2000 for this is using the VD strut model, the vertical and diagonal strut. And similarly, the model is created for the other analysis techniques also. And, uh, and, and I must say that all models are quite capable. They can simulate the behavior of confined masonry walls. As you can see here, the response of the building in both X and Y direction, except the equivalent strut model, which predicted very large capacity, because here the strut is having the compressive properties of masonry. It is unable to simulate the actual failure of masonry. But most of the other models were able to simulate the correct response of confined masonry building. To summarize the various analysis techniques, they are primarily divided in two groups, which can be used for linear analysis. It can be used for nonlinear analysis. Linear analysis, the conventional approach, one can use the standard time method. A standard method can be used to find out the forces, resultant forces, and also it can be used to find out the structural capacity if the limiting values of the strut and the limiting values of the tries are known. Similarly, the various methods like white column, equivalent truss model, the equivalent shell model, equivalent strut model can be used as using the linear analysis to find out the force in the members. The nonlinear analysis, depending upon the input, what are the inputs required. So generally two major inputs are required. Either the input can be in the form of the global response, the load deformation curve, or the input can be in the form of the material response. And using these two inputs, one can also use the various analytical technique to find out the complete load displacement response of confined masonry walls. So in the next part, so talking about the design, so I'm not going to the details of various design clauses of all these codes. So these are some of the important codes, and there are some more codes I have not included here. And there are some of these important guidelines. Of course, this list is not complete. There are other guidelines also available. Now, all these codes have almost common fundamental principles, as Professor Bazev has also said, and they provide the various design guidelines, the various design equations, depending upon the structural behavior, depending upon the various failure modes. So I have shown here some general formulation where the vertical loads are generally considered as a summation of the contribution of masonry, contribution of tie columns, and for the lateral load, for shear and for flexure, there are different set of equations. Now, few code considers the contribution of tie columns, whereas few codes do not consider the contribution of tie columns in a very explicit way. So various codes have a different level of approximations, and the codes provides various guidelines for maximum slenderness ratio, maximum aspect ratio, the wall thicknesses. However, there are some differences in the codes, especially related to the limiting values of dimensions, especially related to detailing of tie columns. There are different examples also, as discussed by Professor Brizev, that there are few differences. So what we did recently, that to compare that what level of safety factor various codes has considered in design shear strength and in design flexure strength of confined masonry wall. So we compared various codes by using the 12 walls which have been tested around the world. So randomly we have taken 12 solid confined masonry walls from different literature, from different studies. And here it shows the estimation of the design shear strength. And so one can see that comparing about 9 codes, that different codes have a different prediction of the design shear strength, the design level of shear strength. Few codes have given a large design value, and where a few codes have given a quite a smaller design value. And if you want to compare the safety factors, so one can compare here. So this curve shows the design to experimental strength ratio. So if it is more than 1, which shows that the code is giving unconservative results, which mean unsafe design results. And if it is less than 1, which shows that the code designs are safe. So what we found out interestingly, that if I compare the design value with the maximum experimental strength, then the ratio comes out to be 0.15 to 0.92. If I compare the design value with the critical capacity or the cracking strength, then in some cases, some of the codes have given the unsafe design results. And mostly in the case of the flexure also, maximum many of the codes are giving unsafe design. So so in conclusion, that some codes provide considerable safety margin, whereas some codes do not provide considerable safety margin. And the reason could be because the codes are very specific to a certain region, and many codes are also of a prescriptive nature. Maybe because of that, the codes have such a large variation in the design safety values. Now, another burning issue which is there is regarding the contribution for different elements of confined masonry. Tie elements, or how much the force will be taken by the tie elements, how much will be taken by the masonry walls. So we looked into various analytical approaches or predictive equations, and there is no consensus among the researchers also regarding the contribution of tie elements and contribution of masonry walls. As you can see from this figure, so the contribution of a tie column, for an example, it varies from 5 to 55%, which is obtained by using different equations. And the design codes also differ a little bit on the contribution of tie column. Few codes explicitly suggest the design level of forces for tie columns, whereas few codes do not suggest anything regarding the design of tie column. They suggest some minimum reinforcement, or some equations are given to find out the design level of the design reinforcement for tie columns. So it is important also to explore and to define that how much force is required to be designed for these tie columns. And I would like to conclude with a lot of research is going on worldwide, because the confined masonries are now becoming popular, and now they are coming up as alternative options of unreinforced masonry, especially for school buildings and for the low-rise buildings. However, a lot of research is required, additional research is required to fill various gaps. We need a more experimental and numerical research for better understanding on aspect ratio and for various other parameters, especially considering the different variation in material in construction methodologies. Still, the comprehensive numerical models are not fully developed. We need to develop a proper numerical model which can consider suitable interaction, which can be used for the multi-story confined masonry buildings, and which can also consider the effect of openings. A better understanding is required, especially on the behavior of tie columns, because we have seen from the past experimental and the past earthquake reports also, that post-earthquake report, that the tie elements, poor design of tie elements can also result in a sudden failure of confined masonry walls. And of course, as Professor Brezev has also said, that many of the codes have not addressed the issue of openings in the confined masonry walls, and we need to have a more experimental and numerical investigation on confined masonry wall with openings and effect of these openings on the response, on the lateral load response. So the overall objective is to strengthen the design codes and the guidelines, so that we can ensure the adequate level of performance from confined masonry walls. This is an important publication which we have published by collaborations, various collaborations. And I will first of all like to thank Professor Dina and her team for inviting, and also to take an initiative on promoting the confined masonry, and especially for the school buildings and for the low-rise constructions. I would like to thank my collaborator from IIT Guwahati, Professor Hemant Kaushik, Dr. Monisha, and the PhD student at IIT Patna. Of course, my mentors, Professor Rai, Professor Brezev, and Professor Jain from IIT Kanpur, IIT Gandhinagar. So thank you all. Thank you for your kind attention. And if you have any questions, we can discuss.
Thank you very much, Vaibhav, for this very interesting and in-depth presentation. It certainly raises many questions. You have provided answers, and there are indeed questions for you in the Q&A facilities. So maybe because we are running a little bit late, if you can look at the question and attempt answers by writing. In the meantime, I will be very happy to give the mic to Svetlana, and she will introduce Professor Juan Jose Perez Gavilan. Thank you.
Okay, can you hear me? It is my pleasure to introduce Professor Juan Jose Perez Gavilan. He is a research professor at UNAM, Universidad Nacional Autónoma, Mexico. And he has spent many years working on confined masonry research. He has been collaborating in many international groups on different publications, and is one of the most active researchers in the field today, particularly in experimental sense. I would like to welcome him and invite him to to share his screen and presentation, if possible, within 15 minutes. I believe that is the time frame. Thank you.
Okay, thank you, Svetlana. Let me this screen.
You can see your presentation. Yes, thank you.
Yeah.
And if you can move it to slides.
Yeah, I was trying to. Okay. It's because I cannot see the bottom. Okay, but I will try to go with this as
Okay.
it is. And so thank you very much for the invitation. And I'm very pleased to have the chance to talk about experimental work. And first of all, I would suggest a couple of publications in which myself and Professor Svetlana worked with other colleagues and research this topic of experimental research in the past. And also another review paper that is published before, but more focused on European masonry, and is that one for Marquez and Lorenzo, and are good sources of studies and have a lot of references that would be useful for everybody. So let me start. Put this away. I would like to mention this research investigation from Professor Melis, a very well-known researcher in Mexico, in that for many years initiated the investigation in confined masonry and produced this research report that is unfortunately is just a version in Spanish, but summarizes at least 10 years of experimental work in which he addressed many of the basic topics that still are part of our construction code in Mexico, such as mechanical properties. He researched these extensively. And then he tested many full-scale walls subjected to lateral loads, and researched the shear strength and these of these masonry walls, and provided one of the this expression of shear strength that still is used in the Mexican code with a few modifications, but basically is the same expression that is still being used in the code. This is a 1979 research report that is very important. And he also researched flexural strength, displacement capacity, and provide many design provisions. As I mentioned, he initiated a long tradition of research in confined masonry in our country and in our institution, the National University in Mexico. Then let me go through one of the, probably one of the first things that were researched experimentally was this idea that how the shear forces are resisted by the masonry walls, in particular confined masonry walls. And this is shown here as a compression strut, and the cracking usually appears parallel to this compression field, so to say, and then by pure mechanics, we know that tensional stresses show up in the perpendicular direction of the strut, and so this is the strength that needed to be researched. I mean, the tensional strength of the masonry, and a lot of work was in that direction. Initially, with the so-called Brazilian test, there were adaptations of this idea that is used for concrete, and they initially started with these discs that were tested in compression, and Professor Melli and other of his students, Professor Reyes, then changed this idea of the disc and changed it to more easy to test wallets, and did extensive research in the sense that to relate the so-called compressional diagonal test with the resistance in the walls. Yeah, and regarding the materials, he also make hundreds of tests of the different types of materials in the country, and find expressions, for example, to relate the elastic modulus with compressive strength of the masonry, and all these piers and wallets provided the mechanical properties of the masonry that finally were so have the chance to put recommendations in the code that really worked and were a very large study, mainly experimental. More recently, I had the chance to look at the shear strength formula that Professor Melli gave in that research that I just showed to you, and we researched the effect of the aspect ratio in the walls, and a study was conducted experimentally with full scale walls with different aspect ratios, and it was found how this parameter needed to be considered in the formula, as basically long walls resist more than the walls that initially were considered well, no, the aspect ratio was not considered before, And it was shown in the graph in the bottom part. It's a shame that I could not show the full. I will, okay.
Hi, Juan. If you click
here.
Yes.
Yeah.
We are
Okay.
almost there, but yeah.
Okay.
Okay, that's good.
And then now the graph can be seen more easily, and it shows how the strength is compared with the formula that provided was with MELI. It was calibrated with mainly with walls that have aspect ratio of 1. And so we compared these results with that of walls with aspect ratio of 1, and then we saw that the formulas need to be modified, and so a different formula was figured out, just a correcting factor for the original formula, and this is the formula that is used today. Other research investigated, for example, the participation or the contribution of the joint reinforcement. This is a topic that was initially studied with masonries of very poor quality, and they, I mean, they get the conclusion that joint reinforcements was not so important, and we research again this topic and saw that the main reason of these findings, the previous finding, was that joint reinforcement cannot provide additional benefits if it is placed in walls that are very poor in masonry. So this was again reviewed by Alcocer and in another student of mine, Cruz, and then find new evidence that the joint reinforcements can be very, very effective, and it can provide additional strength to the walls, but only if the masonry of the walls are of good quality. And so a large investigation was conducted and arrived to new expressions that that are included now in the Mexican code that give understanding of these ideas, and now is very much used this joint reinforcement, also provide a lot of extensive displacement capacity, additional displacement capacity of the walls. And so it's become a very important aspect in the design of confined structures in Mexico. This is another interesting aspect that was investigated using previous results from experimental results from many authors, and it is the fact that how the masonry, the masonry contributes to the shear strength of the walls when the wall has joint reinforcement. And it was found consistently that the contribution of the masonry decreases with the amount of joint reinforcement. And this is an interesting fact, because what is showing us is that joint reinforcement actually produce a more distributed damage in the walls, and in the end the contribution of the masonry gets reduced. And this is an important finding, and it was eventually included, this idea, in the code, where the participation of the masonry was reduced by the amount of joint reinforcement. This is also have done in Mexico and in other parts of the world. This shaking table test. This is mainly to verify our hypothesis on shear strength and to verify the displacement capacity of the structures. This is a major topic because displacement capacity is a very important parameter for the design of these structures. Many times the governing design parameter for masonry structures is the displacement. So we need to constantly verify these ideas, and some allowable drift capacities specified in the code, and investigations have been conducted to check this displacement capacity. For example, I will show just this small video for the benefit of some of the students that are looking for this conference. And this is a half-scale structure, and we conducted this shaking table tests in the Mexican Institute. Yeah, and this is the type of results we have, and we can then we were able to verify the displacement capacity of this structure, and see if our code is doing well. And unfortunately, for the first, there are two types of structures that we tested. One's with joint reinforcement and the other without. And for the ones without joint reinforcement, it seems that the code is agree well with the findings on this investigation. Unfortunately, for the structures with joint reinforcement included, the code specifies larger values than that we observed experimentally. This kind of thing is the value of this experimental research, constantly trying to fit reality is our job basically, and have been very helpful. There are also a lot of investigations around the world, in Latin America in particular. There have been hundreds of masonry walls tested with lateral forces. And there is a colleague in Mexico, Professor Trevino, and with other colleagues that they have this idea of recollecting or gathering all this information in a database, and they were kind with us and shared with us this information. And here I just show part of this this sample of the database is quite large, and we just use part of this data, just referring to confined masonry walls, and have this idea of investigating just an empirical model using just simple regression. It was interesting to see which were the main parameters found, and are consistent with many of our codes. This is the tensile strength of the masonry, or diagonal compression strength, as it is called, the normal strength or stress, the actual stress on the wall, the aspect ratio, and this is the amount of reinforcement and the amount of reinforcement on the tie columns. And these are the main parameters that were found to be important, very important to the behavior of the walls and to predict the shear resistance of the walls. And thankfully for this amazing work of these colleagues, we have this information. Another important issue, for example, that was investigated was in the retrofitting of damaged walls with wire mesh. This was conducted by Alcocer and other colleagues, and they, for example, this is just one of the examples they researched. This masonry wall with opening for a window. The left one is have no reinforcement around the window, and the right one has some tie beams and tie columns around the window. The idea was to test them first, and then retrofit them using this technique with wire mesh. And so they make this test first, and then provide this kind of retrofitting, and they I mean, give some details on how to provide this this reinforcement, and it proved to be quite easy to do this work. And first the walls are repaired, and then this mesh can be installed in one or both sides of the wall. And part of the specification is how to fix this mesh to the wall, and how it should be anchored in the borders of the window and in the borders of the walls. All these details are specified, and the results were very impressive, in the sense that not only they recover the strength of the walls, but provide much enhanced shear strength of the wall. So this was originally thought as a retrofitting technique, but is nowadays used for new structures, and could be very effective reinforcing of the masonry walls. One of the more more recent research is in a topic that Professor Svetlana just told us that is missing in the codes. That is the autoplane strength of the walls. Colleagues from the south of Mexico that are mainly concerned on wind forces instead of earthquake forces have conducted very large and consistent studies in many years, and have provided I mean, they incorporated the flexibility of the confining elements in these models, and they have provided a lot of information that is now being used for analytical models to reproduce this behavior of the walls. And we expect that soon will be specifications in our codes based on all this research of many years of research of these guys, and also work that we have been conducting in the analytical. But thanks to this research, we have information to check our models, and so eventually we will have some specifications for the autoplane strength of the walls. And I don't want to take too much time, but this is the latest research we have conducted, just finished in December last year. And this refers to autoplane walls of partition walls. Partition walls were they got damaged in the latest 2017 and earthquakes in Mexico. And so we found that these partition walls, even though they don't provide any stability of the structure, are very important, because if they got damaged, people have to leave their premises, and so it becomes a tragedy for the families or the occupants of a building to have to leave the building, even when the building is structurally stable and can be used, but because of the failure of this type of walls, the structures become unusable only after many weeks or months that need to be repaired or cleaned or whatever. And so experimental research was conducted to first to have an idea of the strength of these walls, and for that very different boundary conditions and different structuring conditions of the walls. And important information have been found, for example, regarding the spacing of the tie columns, how the tie columns compared with when compared with walls that are internally reinforced with vertical reinforcement. For example, we found that tie columns are much more efficient than the internal reinforcement, and many other parameters that were studied. And another thing that was important in this study was that we were able to find the demand. That is an important thing when designing these walls, is defining what is the force that need to be considered for the design of these walls. And this was also a finding of these experiments. And we will soon provide also some specifications on how to design and construct these walls.
Juan, may I ask you to conclude in 1 minute, please?
Yeah, sure.
Thank you.
Yes, just to finish, just experimental work is just a fundamental work that need to be done to understand confined masonry structures and many other structures as well. And construction and design codes are supported on this data. And also they provide invaluable information to verify analytical descriptions of the models. So thank you very much. And if any questions, we will have a chance to discuss some of this.
Thank you very much, Juan Jose, Professor Gavilan. It's really fascinating talk, and especially clearly you are ahead of the curve with the testing on out of plane stability of confined masonry walls, and all the issues that you have raised with the reinforcement and the reinforcement of the joints is also very important in determining the quality of the confinement. There are some questions for you in the Q&A if you would like to answer them in writing. Now for all colleagues, we have sort of worked through our 2 coffee breaks or through the coffee breaks that we were expecting to have. So we will start the panel discussion. Svetlana and also Sergio Alcocer will join her to lead on the discussions, and I would like all the speakers and panelists, if you can put on your camera and then conduct this we have about 10 minutes. Thank you.
Can you hear me? Okay. Thank you. I believe that Sergio has joined online. Sergio, do you have good afternoon? So we have a discussion among I was one of the speakers, and then Professor Vaibhav and Juan Jose Perez Gavilan. So Sergio, do you have any questions to start with for the panelists or not?
Well, thank you very much, Svetlana. First of all, thank you very much for inviting me to this very interesting symposium. And I want to congratulate for the 3 presentations, very interesting, very comprehensive. And what I think one of the things that I wanted to talk or more to ask is there are some questions in the question and answer box related to whether this confined masonry could be used or could be thought to be a dual system in which you have walls and frames, considering tie columns as columns, and the wall panel, the masonry wall panel, just as a wall. And there is another question related to considering confined masonry as an infill wall. And I think this is very common that confined masonry is not properly understood, that is a load-bearing wall, which is different from an infill wall. And also that the confined masonry wall is not a dual system, in my opinion. However, I would like to hear both of you, Professor Singal and Professor Perez Gavilan. What do you think about this? I think this is quite relevant because there are many questions related to this. Perhaps we can start with the analysis part. Professor Singal.
Yeah. Thank you, Professor Alcocer. So I agree with you. Yes, we cannot consider them as a dual system because their behavior is totally different from reinforced concrete frame with masonry infill. And because what we are trying to do here that the masonry walls will be the primary load-bearing member. And if we design the tie column for a large amount of a shear force, then definitely they will be acting more like a movement resisting frames. And that is what the intent is, that it should be restricted, and that is how the code has been designed, where there is a limit on the spacing between the two tie columns, so that the amount of a shear force or amount of a movement can be restricted in these tie elements. I also believe that considering them as a dual system will not be well justified. But I'm not sure if somebody is going with a multi-story building, maybe with confined masonry, going up to more than 5 or 6 story. So in those cases, when the tie elements or tie column becomes quite heavy, so maybe in those cases, the contribution of a tie elements also need to be considered explicitly for the design purpose.
Thank you. Juan Jose, you have a comment?
Yeah, well, this idea of dual system, we actually in the Mexican code we have thought about these infill walls and how to design them, and because they behave so differently than the frame, and it's very difficult to make design decisions and to make them work correctly, these systems together. And I mean, there are some rules on how to decide when the structure will behave as a concrete structure, and when it could be considered to be behaving as a masonry structure. But these are difficult things to determine, and so it's always difficult to design these two systems together. And but anyways, is economic, so we need to still investigate how is the best way to design them. And we have found that the confining elements are important even in the case of infill walls, and is part of our code now, that should be provided these confining elements even when they are inside a frame. because experimental work have shown that infill walls become very unstable out of plane when they start to crack, and confinement gives them additional stability out of plane. And so I don't know if I answered the question. I just think about this problem of having these two systems together. And but again, I stress that confined walls per se are quite different from infill walls, and they should be designed very differently. One of the main differences is that infill walls do not resist axial forces, so are quite different from the confined masonry walls.
Thank you. I guess the main confusion comes, just a second, just 1 second. Maybe the confusion comes when we talk about struts and strut and ties and things in confined masonry. People may think that, okay, we already have a strut in an infill wall, so we can treat infill walls like confined masonry. And I do think that confined masonry works as an infill wall at very large deformations, at very large drifts when you have a lot of deformation in tight columns. Then you have this compressive stress field within the masonry, and then you can sort of claim that the confined masonry starts working as an infill wall in that sense, but that's for very large deformation. Anyway, that's me. This is Lana.
Yeah, I would like just to add something along the same lines, but talking about different system, which maybe I would suggest to discuss in some other situation. So another system that I learned has been used in Mexico as well as Chile is another type of hybrid system where you have a combination of confined mason and reinforced concrete shear walls, which is also a hybrid system. And to me, it is a system that makes sense because let's say even applications in India, people are seeing a limit to where we can use confined masonry in other countries. So I feel that probably a discussion or a topic of one lecture, now we don't have time to add new lectures or presentations here, but should be these hybrid systems. But my personal preference would be to go in the direction of combining. So maybe if you just have a short comment about whether this has been used, since both of you are from Mexico, has that been used, and is that what is experienced with that system? And then maybe move to another. We don't have too much time, unfortunately, for panel. So maybe a short comment on that.
Yeah, sure. Well, this indeed is very much used in Mexico, and not only to provide extra shear capacity in the structure, but also, as I mentioned in my presentation, one of the main problems with masonry structures is drifts, I mean, lateral displacement. So these concrete walls provide this additional and restrict the displacement of the structure, so that the masonry part of the structure do not get quite damaged because of large displacements. So they work very well together, have been used for many years now in our country, and I think is a good solution. Have behaved well. It doesn't mean that it doesn't have some problems to solve, but in general, I think it has been a very workable, very usable and solution for many structures, particularly in Mexico City.
Thank you.
Let me just one thing, Svetlana. I think this combination of concrete walls and masonry walls have been used for the wrong reason. And the wrong reason is that instead of maintaining a good quality of masonry, that means maintaining a good strength of masonry. We have seen that the strength of masonry is becoming lower and lower, particularly in non-industrialized units, so we call handmade units. And so with those cases, you need to provide an extra system in order to provide enough strength to the structure. So that's when these reinforced concrete walls come into play. And we didn't need them before when we had good masonry, strength, good masonry strength. But now that we have lower strength in particular, as I say, in handmade pieces or units, then we need to resort to the use of concrete.
Thank you. So I think we probably have time only for one more question. Is that right? So should I ask a question or for a panelist, maybe going back to Professor Singal and his presentation, let us talk about this because he talked about design, analysis and design, and I'll focus on design topics. And that is also one of his specialties from his, going back to his PhD thesis, is walls with openings. In your opinion, what do you think should be provisions for walls with openings? And very few codes have them. And but what are your opinion? And that is very important design topic for confined masonry. I think so.
Yes. So thank you, Professor Bizet. So what we have seen, and I think we have done also in the Indian code. So first of all, openings has been classified into two different categories: small opening and the large openings. And the large opening, especially when they go beyond 10%, 15%. So we recommend that if so, some kind of a confinement should be provided around the openings, as some of the pictures have been shown by Professor Gavilan, that for the retrofitting purpose, some confinement is provided around the openings. So if those kind of confinements are provided around the openings, so we have seen that the negative influence of openings on the walls are minimum. So they don't influence the performance of the confined masonry wall. And accordingly, those walls can also be taken in resisting the seismic forces. But if suppose the walls with the openings are not confined, then maybe those walls should not be considered as a part of resisting the seismic forces. So that is what our recommendation, and that is what we have also included in our Indian code. And if they are confined adequately, then definitely they can perform better and they can mitigate the negative effect of opening.
I would like to have just a quick comment about this, because when we think about school buildings, of course, the opening and the windows are major issues, both in size and in location. So, you know, some windows are put towards the top in order to provide privacy within the school classroom and avoid distractions, avoid children looking out of the window, but at the same time providing sufficient light. Or indeed, in other occasions, there are much larger windows than we would use in residential construction. In that case, our experience has told us that has shown us that even when you confine, indeed the span of the window might be larger than the typical span of that the confining rule considers. So what do you propose in that case?
Yeah, so what we have seen, so there is a limit on having amount of opening. So when the opening percentage goes beyond 25%, then even providing the confinement may not work very effectively. So either we have to ignore those walls for resisting the seismic forces. Some additional walls has to be provided which can resist the seismic forces. So and we also recommend that when there are large opening, so it is essential to have a continuous horizontal bands above the opening and also below the opening. So that will minimize the damage, but they may not be able to resist the seismic forces.
Yes, the solution that they have taken in Salvador is to have the opening that is the same length of the wall span, and therefore there are no piers, and therefore there is nothing to damage there, which possibly it's the best solution. There are just the two columns coming up as ties, not as a frame, of course.
But in that case, maybe that the tie elements has to have a spatial confining reinforcement throughout the land. Otherwise, it
Yes.
can fail in the short column effect.
Exactly. Yes, that's one of the issue. And also, of course, because the masonry is concentrated only at the bottom, you can only have a one-story high building. Rather, you cannot have a concrete slab sitting on top. Thank you very much. I don't know if there is any other burning questions. Otherwise, we will move on to the second part of the panel.
I think in the interest of time, it's probably better to move on since we are running late with the program, and maybe later today or tomorrow we'll get a chance to discuss more questions related to the codes, and that is indeed one of the key topics, what is missing, what are the gaps. So we are definitely not leaving it. So any of you who has questions, please leave in a chat box or in question and answer box, and we will answer, and that we'll use it for further deliberations. Thank you very much, and thank you, Sergio, for participating in the panel along with me, and thank you to the speakers. Thank you.
Thank you.
Thank you all for the panel conversations, and we move now on to the section 1.5, where indeed we are looking at example of use of confined masonry in school constructions. What are the application and challenges? I remind the speakers that they have 10 minutes each. Please try to stick to the timing so that we can have then a nice conversation and another panel discussion towards the end. So the first speaker is Erwin Lim.
Hello.
Good evening, Erwin.
Good evening, Professor.
Erwin is joining us from Indonesia, and he will talk about field retrofit of confined masonry school building using ferrocement layer. Thank you, Erwin, and maybe you can introduce quickly yourself.
Okay, thank you, Professor Tina. Let me share my screen. Okay, should be okay, right?
Yes, we are able to see your screen.
Okay, good evening, everybody. Greetings from Indonesia. I'm very glad that can be part of this UNESCO and ERI Confined Masonry Network. I come from Indonesia. Currently, I'm teaching at the Bandung Institute of Technology, and I also belong to the Indonesian Earthquake Engineering Association. And at this occasion, I would like to talk about the retrofit of school buildings using ferrocement layer in Indonesia. And we are very fortunate. We have funding for the experimental study and field project for this time being. We'd like to acknowledge entry of Taiwan for the assistance to the southbound countries by Smart Disaster Management Program, and also our graduate student, Mr. Alfarisi Firdaus, for performing the laboratory test, Ms. Fiona and Mr. Fakri for supervising the field retrofit project, and of course, let Dr. Teddy Boone for his restless effort in creating safer house and disseminating ferrocement retrofit strategy in Indonesia. I would like to divide my outline into 4 parts. First is the problem, and then we want to show some of the cyclic laboratory tests and how we apply it in the field retrofit of a school building, and I will draw my conclusion. So this is a typical school buildings in Indonesia. So mainly they are one-story buildings. The length in the transverse direction is about 7 meters, and we also allow 2 meters for the corridor. And along the longitudinal directions, it's around 7.5 to 8 meters. And usually the size of the tie column is around 15 to 25 centimeters. And the longitudinal bar is usually 4D10. And with the stirrups around D8, and the spacing about 20 to 25 centimeters. Many school buildings were built in the early 1980s to 20s. So mostly single story. Per 2012 census is around 85%. And as Professor Svetlana mentioned earlier, indeed, there is no official confined masonry code available in Indonesia. But we are fortunate that many guidelines from the Ministry of Public Works, NGOs, and individuals are available. The earliest version I can find is the Details Manual by Professor Teddy Boone in 1978. And later on, we have technical guideline from the Ministry of Public Works 2002. And we also can find many guidelines made by the NGOs Build Change and Save the Children. The typical issues for the school buildings with confined masonry is the integrity. As we can see in the photo here, mainly we lack of the confining element, vertical and horizontal, and also especially at the triangle shape at the top part. Usually, when we do the earthquake reconnaissance study, it will fall down. Other issues are the material quality. As we can see that in the left part, the quality of the brick wall is not unified. We don't have code for this. So this is like a homemade. So we go to various island, various city, they have a different strength. And also with the, for the steel reinforcement, usually they use a very small size and large spacing. And not to mention is the issue of the detailing. Usually the confining column and confining beam, they are not interconnected well, both at the top and at the bottom. So in summary, the existing school buildings are seismically deficient in many aspects. Hence, retrofit is needed. We do laboratory test for this one. So we test 3 specimens. The first one at the left part, the red one, we call it the so-called poor detailing. So the confined, the tie column and tie beam, they are not really interconnected. So the anchorage length is not sufficient. And using this poor detailing, we try to put the so-called ferrocement retrofit, indicated in the green color. And in between, for the sake of comparison, we have the standard detailing. So the detailing of the tie column and tie beam are good, and also we provide anchorage between the tie column to the masonry wall. This is the photos of the specimen with ferrocement. So we kind of like warp all the specimen, all the wall with the ferrocement layer, and then we try to overlap and make sure that the sandwich effect between both sides of the steel wire is effective. And this is the hysteretic loop that we can find. For the port detailing, the maximum strength that we can find is the red one, around 37 kilonewton. But if we put ferrocement, it can increase up to the 190 kilonewton. So it's about 4 times higher. And we can also see from the energy dissipation, the green one is much better compared to the red one. So we are very confident that this is one alternative that can be used. And we try to create a very simplified shear strength equations. So the shear strength is, we say that it's a summation of the masonry wall and the tie columns. And we try to calibrate the ERI manual. And I just understand that it comes from the Professor Mary 1975 research. It's the alpha M. Alpha M is used in the ERI is 0.5. Here we try to calibrate using the Indonesian tests. We found out that if you use the poor detailing, then the alpha M is only about 0.245. But if you can have ferrocement retrofitting, you can increase up to 0.425. So using those facts, we continued with our field retrofit to the school buildings. So we try to totally we have 4 school buildings retrofitted in this project, but I would like to only present one for this occasion. So as we can see that in the perpendicular directions, with the blue one, they are mainly hall intact wall, so they are very effective. But in the longitudinal directions, the red one at the back side, the opening is small, so usually around 20 to 30% opening. But at the form part, because we have wall, we have a door and windows, so usually they are not effective. So we would like to confine we would like to retrofit these school buildings. So our idea is like this. So first, if you apply the ferrocement layer, then as we mentioned earlier, we can increase the alpha M factor from 0.245 to 0.425. In addition, because the poor tie column and tie beam detailing. For the existing part, we doubt that it can have any redundancy or it can reach any overstrength. So we put penalty of 1.5. But once we warp the tie column and tie beam together, make sure they are continuous, then we think that it can increase up to 3. So we can reduce the force demand. And using the DCR ratio, we can reduce from 1.6 to 0.6. So we can say that it's okay for the retrofit part. And this is the photos from our field project. So first, we try to remove all the tiles attaching to the walls. And then we try to put the ferrocement layer. So first, at the column, we have to make sure that we extend the wire mesh from the foundation up to the beam at the top. So some parts of the tiles and at the ceiling need to be broken. Next, on the wall, we also put the ferrocement for the whole wall, and then we install and fix on the both sides, creating sandwich effect, and then we allow 10 millimeter cover to the wall. And especially for the side walls here, as we can see at the left part, the triangle shaped one, we also warp the whole wall to prevent it from the out of plane failure. And after that, then we apply the plaster layer, 10 millimeter in thickness, and then the mixing ratio is 1 part of cement combined with 3 parts of the sand. Of course, the amount of water is very tricky, and you have to have a very good supervision for this part. And finally, after all is done, then we reinstate the whole square building to the original shape. And our estimated cost is around 20% to 40% of the new constructions, depending whether you have to retrofit the foundation or not. For this case, we don't need to retrofit the foundation, so it's quite cheap, around 20 to 30% of the new construction. And I think 10 minutes is past. Let me draw my conclusion. So first, the retrofit of school buildings is a need. And then we don't have a code, but many guidelines on good practice are available. And we think that the ferrocement can serve as a good alternative due to its low tech, easy to use in many parts of Indonesia and economics. And one thing that I need to emphasize here is that the strict enforcement in the field supervision is a must, because otherwise then the workers can easily do tricky things. And finally, again, thank you. And for all of you who celebrate Chinese New Year, I'd like to say Happy Chinese New Year, Gong Xi Fa Cai. Thank you.
Thank you. Thank you, Erwin. That was right on time. And I think I will switch on my camera when the speaker has 2 minutes left from the next one onwards. So that's a pointer for you. Next, we have, with the Kyrgyzstan experience of confined masonry schools, Aidaberg Stamov. He is an engineering coordinator for International Association of Experts on Earthquake Engineering. And he's representing also Professor Beglev, who's the president and director of IAE and the professor at International University of Innovation Technologies. Please.
Okay. Thank you very much for giving me a chance to speak on this great symposium on behalf of Kyrgyz Republic, International Association of Experts on Earthquake Engineering, and I hope that you can hear me. Also on behalf of advisors, Lupek Bigaliv and great teacher Svetlana Brzev. So I'm going to discuss, it will be a mostly informative presentation about local experience, practice on let's say complex or confined masonry on Kyrgyz Republic. So design and retrofit of confined masonry school buildings in the Kyrgyz Republic, some practical examples. As you can see, this is the seismic hazard intensity map, which was developed for our current seismic design code from Institute of Seismology. for the PGA values. Next, you can see the applicable current design codes that our designers used for the designing of confined or complex masonry. It's a seismic design code in English and Russian version available. Some local, let's say, building design codes which were developed during Soviet Union time in 1980, 1990, some typical series which illustrates structural drawings for the joint connections of confined masonry walls with precast hollow core slabs. Next, you can see the practice. So in our practice, let's say complex masonry, it's a structure which is load-bearing masonry walls, strengthened or retrofitted by tie beams or columns. We call it reinforced concrete inclusions. And also the masonry is installed with reinforced mesh in horizontal joints, as you can see in the figure, in the picture. Next, you can see some seismic design requirements for the confined masonry structure, for the seismic belts, and for the reinforced concrete vertical inclusions. For the brick grade masonry grade, we use our local GOS standards for the materials, and masonry thickness usually it's 510 or 380 millimeters. So the next one it's about some example on longitudinal load bearing wall, as you can see, and also intersections. Next, you can see the intersections between reinforced concrete precast hollow core with the masonry walls. So the mortar joint is thickness 10 millimeters, cement sand, and the depth of precast slab it's supported by masonry wall for the 120 millimeters. This is the drawing for the precast hollow core slab, typical series. Next, you can see some design examples for the school, which is a typical design project developed on 1980 for the seismic intensity 9 points, existing schools in the Kyrgyz Republic. So next, you can see some facade based on the requirements of our local seismic design codes. The number of storage should be 4, and the limit height should be 16 meters. And for the total length, it should not exceed 60 meters. So here you can see some plan view. As you know, reinforced concrete inclusion should be on the opening side as well, in window or in doors. Next, you can see transversal section view. So based on our local seismic design codes, it's not extended. For the 9 point, it should be 9 meters. For the story height, it should be 4 meters. And also we have a ratio of story height with the thickness of masonry, which is not exceed 12, number 12. Next, you can see some reinforced inclusions on openings on the lintel part, which is the depth of 350 millimeters for the masonry wall. This is the intersection between precast hollow core slab with the seismic belt. Sorry. Usually it is tight reinforcement because our country is located in seismic areas, prone area. The next, it's regarding the precast hollow core slab, which is used mostly for the floor covering, floor system, and roof system. So regarding speaking about retrofitting, so there is a World Bank urban development project. Svetlana Berzev, Lubek Begaleyev was developed a practical manual on retrofitting of schools, typical masonry reinforced concrete schools in the Kyrgyz Republic, in Balakchi and Toktogul cities. So if needed, you can take a look from the presentation in links in Russian and English. So this is the picture about showing some practical in application of shotcrete. As you know, the retrofitting of masonry walls. This building exists in the Kyrgyz Republic, and also it's taken from the manual. So speaking about the challenges and next steps, the challenges, the first thing, it's a numerical modeling of complex masonry, confined masonry school buildings, because due to the lack of practical design and local experimental research, which could be comparative to the international seismic design codes, there is a need to know adequate simulation of effects of beam tie columns, which can act together integrally with masonry wall, their joint connections. Next, it's numerical modeling of precast reinforced concrete hollow slabs. This is to consider the effect of holes and joint connections in masonry walls. And the third one, finally, it's reinforced concrete topping, which should be used in case of increasing seismic safety, shear strength of precast reinforced concrete oracle slabs, which is used in our country. And one thing that I would like to mention that mostly this system, it's used for the schools, for the kindergartens, and residential houses with the story of two or three stories, like 3 meters per each story. So I concluded my part. And one thing I would like to inform as well, all of the requirements on designing of complex masonry, it's included and specified in our local seismic design codes, which is used by our local designers when they design school buildings, for example. So most of the information was taken from this reference. If you would like, you can take a look, but those are in English, sorry, and was developed in Soviet Union. Thank you again for your invitation on behalf of my supervisor, Dr. Bigaleev, Ulbek Bigaleev, for Professor Dina Dayala, Professor Svetlana, and also dear Dr. Aksana, organizer, speakers, and participants. Thank you very much for listening my presentation. I'm finishing. Thank you.
Thank you very much, Hyderabad. Right on time again. I think we do have questions popping up because we have a panel discussion, open discussion after this. We can take the questions later. May I request Professor Daniel Quinn with the Peru Experience School in Confined Masonry, please. Dr. Quinn is a professor of the Department of Engineering at PUCP, Peru. Please, I would like you to invite to start your presentation, sir. Thank you.
Hello, I will look for my presentation, and meanwhile, I have to say thank you all for your kind invitation. I hope the internet connection goes smoothly, but sometimes it's pretty slow. Well, I am a professor at the Pontificia Universidad Católica del Perú. I have more than 30 years and a professor and still teaching masonry.
We can't see your screen yet, and I think we lost you. No, we can't.
It was a elastic code, and afterwards we had the current 2006 code. I don't know if it's already
Daniel,
visible.
now we can see your presentation. If you can share it, yes, exactly. You can put it in. Yeah, perfect.
Yeah, sorry.
Please.
So I'm sorry for the delay. Okay,
Thank
this
you.
is the title. I will talk about confined masonry and non-structural masonry walls in school buildings as Peru. Peru is facing the Pacific Ocean. We have a lot of masonry. We have more than 33 million people. And Lima, the capital city in which I live, more than 10 million. These are the codes I was talking, and we have a new version still in waiting to be approved. The main source of the earthquake are due to the subduction of the Nazca plate, as many you may know. We have a lot of informal construction, as you may see, non-engineering. But anyhow, I have to teach how to do good masonry constructions. We have recent earthquakes in the 20th century, which I have felt myself, mostly in the coast of Pacific Ocean, and some rare are in the Andes mountainous region or in the jungle. Regarding this Nazca, Arequipa, Pisco, Lagunas earthquake, you may see some damage to school buildings. I'm not showing other buildings because that will take a lot of time. And I have to say that masonry in schools in Peru is the most popular construction material. We use them for the confined masonry walls, the bearing wall for axial and other constructions, and also as a non-structural walls that you may see parapets or fences, or not non-structural walls that do not go all the way to the top, and they behave as a non-structural wall. Although they have these tie columns and tie beams to withstand out-of-plane forces. This is my university, one of the buildings, also confined masonry. The governmental schools have these typical classroom buildings, combination of confined masonry walls with reinforced concrete to make a classroom, one after the other, and we can have 2, 3, or 4 classrooms in a row. They can have 2 or 3 or 4 stories, and these are some of those that were damaged in the Pisco 2007 earthquake, but mainly in the longitudinal direction where the confined masonry is absent. Only these RC column frames are the main resistant structure. In the transverse direction, the confined masonry walls behave pretty well in the most of the cases. And we have an issue with the parapets and so on. Well, this is the plan view and some elevation. Typically one-way joist slabs that is being supported on the confined walls and the RC beams. We have longitudinal RC frames with non-structural masonry walls or below the tall windows. And in the transverse directions, the main structural is the confined walls, as you may see. Some bearings frames are also present, but the problem is in the longitudinal direction, these low tall walls, but that don't go to the roof, make these short columns. This happened in the earthquake I was telling you in the longitudinal direction. Please do not think of these walls as confined masonry. These are non-structural masonry, but that affect the structure. In the Nazca 1996 earthquake, we have this issue. The new schools had this damage in the longitudinal direction, producing lot of short columns. And this because the weak flexible RC frames hit the masonry walls, non-structural. And then in the other direction, the transversal confined masonry walls were mostly undamaged. Also, we have these infill walls cases in which they separate from the RC frame. We can see the cracks over there. In the 2001, this earthquake triggered the change in the seismic code. We had new buildings with strong columns in the longitudinal direction, and compared to old buildings, they were still happening. This is a short column effect. The new ones had no damage in this earthquake of magnitude 8.4. This after the earthquake, many retrofit prayers and repair and retrofit projects were done. The emphasis was in new walls and new strong RC columns, as you may see, 2- and 3-story buildings, and also in 1-story school buildings. The idea was to provide a strong confined masonry walls in both directions to increase the lateral rigidity. In some cases, the non-structural walls had to be designed, the separation joints, to avoid the interaction. Also, for 2- and 3-story buildings, we had to eliminate some of the existing non-structural walls to provide strong RC columns and coupling beams. And you may see a result of this sort of retrofit project. Also, the non-structural walls with tie columns and tie beams, but non-structural, had to be designed with wide separation joints to avoid the interaction. This is somehow the plan view. The walls were in these positions to let some windows still being providing illumination to these classrooms. In the 2007 Pisco, we again have this short column effect to all buildings which were designed before the 1997 code, with a lot of damage in this kind of schools. This is a very strange mixed failure we had in this confined masonry wall, and also a lot of out of plane collapses in many fence walls, as you may see. On the other hand, we can see that in the same town of Pisco, which suffered this earthquake, the new school buildings built after the 1997 with strong columns in the longitudinal direction and good confined masonry walls had no damage after this earthquake compared to the other ones. Oh, and to end, I have to talk about recent school buildings in Peru. They are 1 to 3 stories. We maintain the confined masonry walls in the transverse direction and RC strong columns with non-structural masonry walls with specially designed joints to avoid the interaction. And in my company, I also have a structural company. The recent school buildings had this challenge to make fast-track construction, and this construction company said we need to avoid masonry, which is very slow, and we need RC buildings for classroom, which these strong RC columns and infill walls to complete the architecture. So confined masonry work was limited to small buildings and fences like this or non-structural walls. And you may see this is a RC structure with infill of concrete units, or like this one, clay units. And the challenge was to provide stability to this, for out of plane to these new schools, the walls of this school with either reinforced, internal reinforced walls, and also there were the whole length of the school had this perimeter wall we had to evaluate in order not to demolish and had to construct again. What we have to this evaluation, we did this with the current masonry code of Peru. And more pictures of this new construction of this recent 2-3 years ago. more masonry in small buildings and also in the fences. And as a conclusion, I have to say that the school buildings in Peru have behaved very well. In the confined masonry wall have behaved mostly okay. Non-structural masonry wall have provoked these short columns, and they need adequate separation joints and more rigidity. The retrofit projects emphasize the increase of rigidity, which look at these strong columns in the longitudinal direction. And these smaller walls of masonry have these separation joints. The new fast track construction, you may see RC frames and walls is the main construction, and the masonry is mostly infill. And so the confined masonry is devoted only for small new buildings and as non-structural masonry walls and fences. Some of the buildings that were had to be evaluated. So we have these models to analyze and see if they were still available. And also had to do with the same for the fence wall for out of plane actions. To finish, I have to stress the work of Professor Ángel Bartolomé, who passed away some years ago. Many of his work is published here in this blog, or mostly is in Spanish, but I hope you can understand most of it. And this is my lab. I have these lectures on masonry for undergrad and master's students. And I also make a professional design of masonry and structures like this. So I will have to say thank you for hearing me, and success for this seminar. Or
thank you very much. Thank you, Professor Quinn.
Thank you, Danielle, also for answering many of the online questions.
Yeah.
No problem.
I think just to keep with the time, let's move on to the next presentation from Marcos Chavez on the Mexican experience of confined masonry schools. Marcos is a professor in the Faculty of Engineering at UNAM, and he's also laboratory manager of the Laboratory of Structural Engineering of the Institute of Engineering. Thank you and welcome, Professor Marcos. Once again, I shall switch on my camera when you have 2 minutes left. Thank you.
Hello, thank you for your invitation. And let me show you my presentation. Okay. Well, I want to tell you about the work that has been developed in Mexico to evaluate and rehabilitate masonry school after a earthquake. Although this methodology can be applied to schools built with reinforced concrete or steel or any type of structures. This work is under direction of Sergio Alcocer. In this slide, you can see the typical school in Mexico. We have two typical types, as rural or general. The first one can be built with reinforced masonry or steel and concrete slab. The second one built with reinforced concrete and 1 to 4 stories. Although there are atypical schools, built with different materials and with or without technical assistance. This is the more common in rural areas. The typical damage due to the earthquake are the damage to the walls, due to diagonal tension, and damage in buttresses. This is also common to find damage that are caused by lack of maintenance. According to the damage reported during the 2017 earthquakes, 40% of the masonry school present some type of damage. 36% of the one-level reinforced concrete present damage. 64% present damage in two-level schools, and 40% of the schools with still present damage. The schools that suffered the most damage were those that were built before the earthquake of 1805. To simplify the assessment of the existing school, a methodology based on 3 levels of the evaluation was implemented: rapid assessment, intermediate assessment, and advanced assessment. The rapid assessment is through an inspection on the building to determine if it is safe or unsafe. If the rapid assessment concludes the building is unsafe, the intermediate assessment is carried out by structural engineering to determine with more information if the building is safe or unsafe. As a result, structures can be classified as safe, potentially dangerous, or unsafe. The advanced assessment is when the structure is considered unsafe in the intermediate assessment, and through file tests and numerical analysis, the capacity of the damaged structure is evaluated. Also, different reinforcing strategies are analyzed. These assessments are executed in the reconstruction phase. After the assessment, it's important to put a notice in the building to inform the population if the building can use or reflected gases or unsafe. We put the notice green, yellow, or red according to the damage, the level of damage in the building. To facilitate post-earthquake assessment, guidelines and manuals have been developed. They have all been prepared by Sergio Alcocer and his great work team. The first 3 guidelines, methodology, introduction to seismic behavioral structures, and post-earthquake assessment, is used for level 1 and 2 level assessment. The technical guide for earthquake rehabilitation of Mexican school is used for advanced assessment. In this slide, we can see this important technical guide. It's in Spanish, so but this technical guide includes minimum requirements for evaluation, analysis, design, construction, and quality control for the rehabilitation of existing buildings. Moreover, this document is a complement to the Mexican standard and local regulation. All these documents are public and you can download at the link shown in this slide. All information is in Spanish. The technical guide is composed for 9 chapters, and we can see, and I can see, you can see the content. Next, to carry out an adequate advanced evaluation, is recommended to realize a field inspection to collect all necessary information, such as identification of damage, modification, ambient vibration testing to identify the dynamical properties of the building, use of 3D scanner to obtain geometry and find irregularities, core extraction and testing concrete to obtain the mechanical characterization of the construction materials, and identification of the reverse and position, and finally, elaborate numerical analysis fed with all the previous information obtained. In this slide, you can see some examples of the ambient vibration testing realized in many schools, Mexican schools. It's important to know the dynamical properties to calibrate the numerical models of the buildings. Use the 3D scanner to obtain point clouds is very important because we can obtain a detailed geometry of the whole structure and elements.
Sorry to bother Mr. Marcos. I'm going to ask you to conclude, sorry, in a minute. Thank you.
Okay. So, yes. Here, some examples of the core extraction and mechanical properties of the mechanical properties of some schools and some samples of the numerical models. To retrofit in masonry, the main techniques used are adding masonry or concrete walls, jacketing of walls with welded wire meshes covered with cement mortar, adding external concrete buttresses, and well, that's our final comment is a great effort is being made to ensure that the guidelines and models are used for the evaluation and rehabilitation of the school by practitioners, and it also being recommended to avoid set-built construction without technical advice. Thank you. That's all. Thank you.
Thank you very much. Thank you, Marcos.
Thank you, Marcos, and for the interesting perspective from Mexican, which clearly has a very important set of guidelines for the schools, which I think together with the other examples that we are seeing, it would be great to incorporate and to bring together in a single database. This is a little bit also the effort that we are trying to deliver here. I will now like to introduce Dr. Rasana Paramarvateri. I'm particularly happy to introduce her. It's my ex-PhD student and a very good research associate and collaborator on the UNESCO chair. And she will talk about the glossy taxonomy for confined masonry school building, which we developed within the World Bank framework for the Global Library for School Infrastructures.
Thank you, Dina. Thank you, everyone, for your very insightful presentations. My idea is to first understand why we would like to have a taxonomy for schools specifically. As we understand, a taxonomy is a process of identifying certain parameters which can then characterize the behavior of a building. when it's exposed to natural hazards. So in this particular case, we are definitely talking about seismic performance of these buildings. So why schools specifically? Because they are generally built with a function in mind, and hence often have a consistent architecture, and often repeated around a country by the governments once they have certain model buildings. And it's identified that certain architectural characteristics of schools are making them more vulnerable to seismic hazards as compared to other residential and other typologies. And we are aware that certain limitations in terms of technical or economic resources might then affect the ability of the school buildings to respond. So if we have a common language or common understanding of identifying these typologies of school buildings, it's much easier to talk them as a group, and we can characterize their seismic performance irrespective of the region or where they are from. So the idea of developing this typology is also to include these typologies which are very much varying from country to country, and also maybe not completely complying in according to the existing guidelines. So just a few school buildings in confined masonry from El Salvador to Mexico and Peru and other countries. You can see already existing variations in terms of the sizes and the level of confinement and other details. The glossy taxonomy, it's an existing taxonomy system which was developed under the World Bank's Global Program for Safer Schools as a collaboration between the University College London with Professor Dina and Uni Andes in Colombia. And this is a system that identifies these performance of school buildings through 12 parameters, as you see here. In which this can be explained as you see. The first three are the primary parameters, which basically characterize a building into one of the main categories, and the secondary parameters then identify further details of them. So in this, most of these parameters are common to masonry, load-bearing masonry typologies, but with respect to the confined masonry, we will look specifically to three of these parameters a bit more in detail. So with the main structural system, as we understand, is the confined masonry, with the scope limited to the masonry panels composed of rectangular blocks confined by RC confining elements. So there are even variations of this in terms of the material of confinement and also the material of masonry fabric itself. So within this typology, we see there are still existing variations. Say we did have this discussion of hybrid systems in the previous session. So we might find these combinations of confined masonry construction and reinforced masonry construction in one direction, or embedding reinforcement within the masonry fabric, as you see in Indonesia. So depending on that, we can characterize the main typology of confined masonry to further 4 subdivisions. And the second parameter, which is of high importance, is the seismic design level, which we have defined in terms of 3 features. First is the minimum required confinement, which basically identifies your structure is a confined masonry building. It's not an unreinforced or unconfined masonry building. So this is by checking whether your masonry panel has confinement on all 4 sides, which is the very basic requirement. So once we have this, you can then look for the connections as in terms of toothing or double bars at the interfaces, or the connection between walls and roofs, and also the connection between the confining elements. The third feature is the wall density. As we understand from the ERI guideline, certain set of guidelines are identified, which is a minimum level of wall density, which is required in depending on the seismic intensity zone and the type of building, in number of stories and so on. So with these criteria in mind, we have defined in glossy 4 design classes from poor to high. We will explain each of these in the coming slides. The first one, the poor design, is where you are just satisfying the minimum confinement ratio. In low design, you have as an additional feature, you have good connections. In the medium design, you have better wall density or sufficient wall density in terms of additional confinements. And in high design, all this is required criteria are met, including the additional horizontal bracing for the flexible roofs. So in site, we can identify differences in existing buildings, as you see here, depending on the availability of quality of connections and the type of confinement around the openings and so on. So here we identify a poor and high design example cases. So with these 4 categories, we can then have a simplified approach which can almost visually identify and categorize a building into any of these 4 design classes. So as an example, we just looked at a sample building from Guwahati, India, which was modeled on applied element method basis platform, and which was produced with poor connections and better connections to represent poor and low designs, and which was then improved to have better confinement to have a medium design, and then improved further to give a horizontal bracing to have a high design element. So each of these were showing varied behavior. As you see here, for poor and low design, we see very local, out of plane, premature failure of these walls, which are before mobilizing any of the rest of the building capacity. While for the medium design and the high design, we start seeing but much more global behavior of building, arresting any local failures. And this is also observed in terms of their capacities, the longitudinal lateral load carrying capacity and displacement capacity. And the last 2 parameters are the wall panel length and the wall opening size. As we have seen from the previous discussions, we understand how much these elements can also have an influence on the seismic performance. So the wall panel length is a factor that actually determines the out-of-plane failure mechanisms. So it is necessary that we restrict the span between the columns, the tie columns, which also depends on the wall thickness. So if you have a thicker, full brick thick wall, the glossy system is now proposing to have a 4-meter limit for a short span, and beyond that will be a long panel. And between national codes, there is variation of this limit from about 4 to 6 meters. And cross walls is also another criteria, but this is not considered for the wall panel length determination, as this will come as an after effect of the wall density criteria. So as you can see, it's a feature that is easily identifiable at site. And similarly, the wall opening size, and we have had this discussion already that this is identified as a field of further research, and how to better improve the behavior with in walls with openings. So as we understand, less than 10% of wall area does not affect significantly, but beyond that, this can be a serious issue. So we have identified 3 possible classes of wall opening sizes: the small openings, which are definitely less than 10%, or if it's a large opening, whether it has a confinement or not. So depending on that, we can then characterize and classify the buildings into classes. So within these buildings, this is an example of how we can classify them according to the wall opening sizes. So for this particular building, if we apply this taxonomy, then you can have these alphanumeric codes for each of the parameters, including the ones that we discussed in detail, and produce the kind of taxonomy strings for each of these buildings. And when you classify and categorize them, it's easier to identify the typologies that are more predominant in a region on which you would want to have more interventions. So I would stop my presentation here. More details of this classification system specifically for confined masonry is available here. And thank you very much for listening.
Thank you very much. Thank you very much, Asana, for sticking with the time. And maybe we can give the attendee 2 minutes of break, and then we will start the panel discussions. And the panel discussion will be monitored by yourself and Anna Pavan. Thank you. So everybody, if you want to grab a cup of coffee or stretch your legs, you have 2 minutes.
Dear Dr. Afsan, are you here? Can you hear me?
Yes, yes, please go ahead.
Thank you for presentation and invitation again. And actually, the presentation that you showed before, it is interesting because we use it in our World Bank project.
Yes.
So the taxonomy.
Yeah.
And I don't know, maybe you know this person, but I work with Jin Jibu. It's a short local consultant from the ERIC project.
Yeah.
Just to
Yes,
let you
yes,
know
yes.
that.
We did work with them before. Sorry, while developing the original taxonomy for masonry and RC structures.
Yeah.
Yeah.
And if for future presentation you may use, there is some information related for the Kyrgyz Republic for the masonry schools.
That's very helpful. Yeah.
Like
Thank you.
complex masonry and like let's say large panel buildings, large panels buildings. Also there is some one-story school buildings which is retrofitted by buttresses, by ties, metal ties in interior school building, inside of school building. So it will be interesting to you to see.
That's very good to know.
I just shared the link.
Okay, that's great. Thank you.
So in the main page, in the main picture, you can see the school student smile in face of school building, local school building in Kyrgyzstan. So thank you.
Thank you. Hello, everyone. Welcome back. Hi, Anna. Are you online yet?
I am. Hi, everybody.
Hi, Anna.
I'm gonna put my video. Hi.
Yeah.
Sorry, it's very dark.
No, it's okay. we can manage to see you somehow. Yeah. Hi, Anna. I welcome Anna to moderate this panel. We will have a discussion with the speakers on school construction in different countries in confined masonry, and I hope we will still have a few minutes for the audience to have their questions answered. So let's start the panel. Would you like to go first, Anna?
Yeah, thank you very much. Well, first of all, thanks everybody that has presented today. It has been super interesting. And especially the last session on schools, for me, it was, for the type of job I'm doing, it was very, very interesting. I would probably break the ice with a critical question to all of you. So we've seen that confined masonry could work for school if it is well built. We've seen that we have design codes in some parts of the world, design standards or guidelines in other parts. So how do we take it out there? How do we spread the knowledge that you've shown today on good construction practice, good retrofit? How do we go in the most rural part of the country, in the islands, in the smallest island of Indonesia, and avoid seeing what Dina showed on Turkey and Morocco? I suppose I will start from this question. Thank you.
Would anybody like to take the question? And also, I mean, just to add to that question, are we, like when we said we have these guidelines or codes available, do they have specific mention to schools, or are we adapting existing confined masonry codes to schools? And how do we then take it to places where this is not available, as Anna questioned?
Okay, hello, Anna. Let me start first. Again, I am speaking from my perspective in Indonesia. So we don't have any specific guidelines for confined masonry for school buildings. So we use the general guidelines. And for Indonesia, Indeed, the challenge is the field supervision. I think in some of my experience, the workers know what to do, but sometimes they don't want to do it. Just for instance, to make the 135-degree hook, it's just like putting a the seat belt in our car. The one click, and it matters for our life. Just put just another 35 degree, then it will save life. But it's very, very hard to push the worker to do the construction. So what we need is very strict enforcement in here.
May I add something, please, if possible?
Yes, please.
I also agree with Professor Lim. In all countries, I think I can also add a technical supervisor mostly know how to deal with construction works, even if designer or even if a scientist or researching is doing the design. There is one challenge related with the, let's say, developed countries and underdeveloping countries like our country, Kyrgyzstan, Tajikistan, Central Asian countries. As you show before in my presentation, we have other, let's say, norms and regulations for the seismic design of this kind of buildings. For example, sorry for this, in your countries you use like cast in situ monolithic slabs. In our country we use precast slab because it's economic, and this kind of also like vulnerability. So I think in my opinion, it would be good to make a comparative analysis for these codes, for these typologies of, let's say, CIS countries, Soviet Union countries, and together with, I think, developed countries for the codes and for the numerical modeling, because I see you use it quite different analysis. We use it quite different analysis. So just to make a comparative analysis of the codes. Thank you.
So lastly, I must say, in Peru, more than 20 years, we have schools as essential buildings. So this means they have to be designed regularly, without any irregularity in structural, in plan and in elevation. Also, the important factor is 1.5 respect to common buildings. And as these are costly buildings, usually they are many people that try to compete, and it is chosen the better contractor. And also there must be a supervisor and qualified workers. So the way to spread this, educate the authorities, educate the mayors, educate the people, educate the teachers also. So these type of conferences, and like I do many of these in Peru, and try to disseminate all these code specifications to students and authorities. Thank you.
That's a very good point. Yeah. Yeah, it also comes to my mind, like we have this technical course. This course is covering the behavior of RC structures, steel structures, and I've seen much less in terms of masonry. Maybe it varies from country to country where there are masonry structures very prevalently, but that might be something to read together with what you just suggested, Professor Daniel. Yeah, including the knowledge of confined masonry and masonry structures in the curriculum of engineering institutions. Yeah.
Yeah, and if I may add, and actually I turn the question to all of you that work there, retrofitting is often left out of I didn't study retrofitting of building when I studied engineering, so I think retrofitting of existing structures, masonry, steel, concrete, if we want to expand, should probably take bigger part probably in in the curriculum, what we study, I don't know, as students, as future engineers, probably will help.
And I wanted to ask, if we have these existing codes, and how about the retrofitting codes as well? Like, do we have specific guidance already available for retrofitting of schools?
Well,
We have in our country, but most of them in Russian.
The next masonry code in Peru will have a chapter devoted to repair and retrofit, but only guidelines, because there are so many issues to address in a retrofit that it cannot be in a code. So we have students' theses which have been presented in different conferences that show how to retrofit with wire meshes, like the Mexican experience of Professor Alcocer, and also other meshes have been tested in university laboratories, but no way to include them in a code.
Thank you. You're mute.
If I may ask, do you think, apart from code and proper engineering regulations, like Erwin said, like in the builders here in Indonesia know how to build well, they just don't want to do it. In other parts of the countries, they might not know it, and they might not be able to read 2D drawings or detailings or codes or regulations written in a more formal, let's say, solution way. I wonder if, from your point of view, as part of the spreading knowledge and this campaign to prevent rather than act after, do you think some builder's guide and lower level, like Professor Marcos Chavez showed rural construction, and he mentioned that very often in Mexico, they're not supervised by proper engineering input or architects or technicians. So I wonder, do you think like a less formal type of guide directed to builders, like a simple language that with simple detailing, do you think might be part also of the way of spreading this knowledge that you showed today?
Yeah, in fact, I think like Professor Svetlana outlined earlier, in Peru or in other countries, they have like a cartoon, so very illustrative.
Yeah,
In Indonesia, indeed, Dr. Teddy Boon, he also made like a 3D makeup, 3D mock-up for how to put the layer and things like that. Yeah, I think those are very easy to use and easy to understand tools for the builders, I think.
I think, yeah, it's like it goes in two ways, in the sense that we need to have these design guidelines, which is very much more technical, and the building or construction guideline, which is a bit more on the baseline. So yeah, I think there are available guidelines in some countries, at least in this regard, which are catering to both the audience. Professor Alcocer, you raised your hand earlier.
Oh, well, I just wanted to convey very briefly the experience that we have had in Mexico. We developed a chapter on seismic rehabilitation of masonry structures for the 2004 standard or code. And then we were forced to develop a guideline specifically for school buildings after the earthquakes in 2017, because we had a lot of damage in school buildings, whether in rural areas or urban areas. And we have taken that guideline now as a standard for rehabilitation of buildings in general for Mexico City, but can be used for other buildings. And it has all kinds of techniques that are applicable to concrete, masonry, and steel buildings. Unfortunately, it's in Spanish for those that do not speak Spanish, but can be now translated very easily with Google Translate. But what I want to say is that there is a lot of experience that we have got from the field, from the laboratory, for tests that many people have conducted in Mexico and elsewhere. And I think these kind of guidelines are available for anyone to be used. And then just answering the question or the concern that Anna raised about what to do with the rural housing or rural school buildings. As it was mentioned, leaflets, a small documents pretty much developed based on cartoons, have provided very relevant information for what we call beneficiaries, which are people who actually themselves will repair or strengthen their house or their school building, and with very simple methods, very conservative methods, so that they can be easily applied in the field. So I think that experience is there for many countries, and Svetlana has doing a great job, and Dina as well, spreading this information. So I think it's a matter of a distribution effort more than developing themselves, because I think we already have many of those simple guidelines. Thank you.
Yes.
Actually, yes, very recently, within the Berlac project that I mentioned at the beginning, we have seen similar descriptive guidelines that has been developed for Guatemala. It was not just for confined masonry and for masonry, not specifically for the school, but it encompassed more, both, which I think very important, both the configuration and the process of building. Therefore, it's really a step by step, and what should be done first, and how do you actually end up with a resistant building. And I think it was done in a very simple way, which is very useful. But yes, I agree with Sergio. There are many different guidelines out there, and most of them come from direct experience. They are not just developed at the desk. So it's very important that these are further disseminated. And I would just like to say that if anybody has knowledge in any of your country of these guidelines or these documents, and you want to send it to us, we are planning to put together a database, and where possible also to see how we can translate it and make it more accessible to other countries. Thank you.
And with that, can I just add that, because I just presented the brief of the glossy taxonomy. So if we have confined masonry schools database in different countries that you're aware of or you are able to access and share, it would be very helpful for us to also test the taxonomy, like is it covering all the requirements or we need further modifications and so on. So we would be very happy to work together on that if you have database of schools from your countries. Thank you. We see some hands up. We are running over the time, but if you don't mind staying and continuing the discussion, please unmute yourself and ask if it's a question. We will stop maybe in another 3 or 4 minutes.
Jamal, you had your hand up. Jamal Lion is trying to connect with the audio. Jamal, yes, please.
Yes. Good afternoon. I'm Professor Jamal Ilayan from King Saud University. I want to ask about the masonry structure will be only in masonry. I mean, if we put firm concrete firm, reinforced concrete firm, it becomes as concrete structure, not as masonry. Why we call it masonry structure? This is my question. Thank you.
Yeah, this is really, it's the reinforcement frames or the elements we see in these buildings that you've seen in all the photographs. they are basically to confine or just to tie the masonry together. They are very different from how a RC frame acts under gravity or lateral loads. So that's basically I think the very basic difference. And we still treat the confined masonry buildings as load-bearing masonry structures, because the masonry is very much part of the load-bearing component of the structure. If anybody else wants to add, please.
Unmute, can you hear me? Okay, thank you. Sorry. So I wanted to add, it is really important to understand, I believe most participants here are familiar already with confined masonry, but this is really one of the burning questions and dilemmas. What is the difference between confined masonry and reinforced concrete frames for many other people who have not worked in confined masonry? So the main reason is that reinforced concrete frames, as you probably know, those who are into concrete construction, have performed poorly in many earthquakes. Recent earthquakes in Turkey are one of the examples. And confined masonry does not provide solution for all buildings. Cannot build 20-story building in confined masonry, but at least for low to mid-rise buildings, it is a very good alternative to a reinforced concrete building. But understanding, as Aksana mentioned, understanding the difference is the key. And of course, there are several publications and other that explain that, and some papers that compare those two typologies are also available. Recently, I've co-authored one in Buildings Journal with colleagues from Serbia. But anyways, it is known, but it is critical to understand that confined masonry is load-bearing masonry construction, and these reinforced concrete elements are just reinforcement to masonry. They're not, they cannot stand on its own. That's all. I hope a little bit I helped a little bit.
Thank you very much, Svetlana. And Anna?
I have another curiosity from Peru, Mexico, Indonesia, Kyrgyzstan. If you see any effort from the Ministry of Education together with the academia and the government in general to put retrofit of existing structure at the top of the agenda before the next earthquake or before the next disaster. I wonder how it is going around the world, this kind of priority.
Would anybody from Lee, Erwin, or Eidelbeck, or Danielle, do you want to answer, Danielle, please?
Well, not due to earthquake, but we had the phenomena of El Niño, which destroyed many cities, schools in 2018. So we have a strong reconstruction program in all these affected, especially in the schools. And United Kingdom team was invited to supervise, provide guidelines, and we had this experience. We have some pictures I showed are from 10 schools that were retrofitted, and there are many more with this background, with a strong frames, strong walls, and good supervision, and that will be great. But for earthquake, not so much.
That's very interesting, actually, that basically you are saying that windstorm have caught more interest in the eyes of the let's say, government and than not the earthquake. Although the earthquake, to a certain extent, is more common, certainly in places like Peru. Thank you very much, Anna. Thank you, everybody. Sorry, we are already 15 minutes beyond our limit. If there is any last burning questions, anybody's raising their hands. There were a lot of interesting questions in the question and answer. I hope that most of you got a written answer that is satisfactory. If not, we will have more time tomorrow. Of course, we are coming back at the same time for another 3 hours of reciprocal entertainment on confined masonry, which today has been very, very interesting from my personal perspective, but I hope also from everybody else. If you would like to switch on your camera just for a minute so that we can immortalize ourselves all here attending the symposium. I'm sorry that the many attendees in the webinars, the audience, this Zoom is not democratic enough to let everybody switch on their camera. But we really thank you very much for being present today, and we look very much forward to all of you joining us and more tomorrow at the same time. It's 1 o'clock UK time, and I'm sorry, we are GMT +1, so make your computation to what time will be yours at home. Thank you again, and enjoy your evening, morning, day, wherever you are, and night for many of you. And thank you for keeping with us until the last minute. See you all tomorrow. Bye-bye.
Oh, Tim was it?
Tim? Maybe it was just clicking off and he went on the